The AI boom looks like a chip story. Its heavier bill sits outside the chip, power lines, transformers, cooling loops, and the metals inside them. Copper gets the clearest direct lift. Silver and gold matter inside electronics, but at a radically smaller scale. And the next constraint may be the grid, not a mine. The reason this reaches the metals market is simple. AI keeps adding dense electrical load. The International Energy Agency expects global data center electricity use to rise from 485 terawatt-hours in 2025 to 950 in 2030. That is a build-out of physical capacity, not a line of code. The shape of that load matters as much as the total. The IEA says AI server power density increased 11 times from 2020 to 2025. A data center is becoming less like a warehouse full of ordinary computers and more like a concentrated electrical machine. Dense load changes which materials matter and where. Start with the metal that carries the whole electrical system. Copper is the most direct AI infrastructure metal because it follows power. Think cable, bus bars, power distribution, backup systems, cooling hardware, and the connection between a campus and the grid. The GPU is tiny. The electrical neighborhood around it is not. That is where tonnage accumulates. S&P Global's 2026 scenario puts the scale in focus. It forecasts copper demand tied to data centers rising from 1.1 million metric tons in 2025 to 2.5 million in 2040. Treat that as a scenario, not a promise. Still, it tells us where AI turns into bulk. Metal demand, infrastructure, not just the silicon package. The useful metric is intensity, not a single dramatic factory number. In the same study, non-crypto data centers use roughly 30 to 40 metric tons of copper per megawatt. Designs differ. Redundancy differs. Location differs. The point is that every extra megawatt brings a substantial physical bill before the first model starts training. Copper is not alone. At high voltage, a campus often meets transmission rather than neighborhood distribution. S&P Global notes that this grid connection can have more aluminum impact than copper. Aluminum is the overhead grid metal in this story. Copper is the dense electrical metal inside and around the campus. Different layers, different demand signals. This is also where the easy copper narrative breaks. S&P Global projects total copper demand rising from 28 million metric tons today to 42 million by 2040. AI is one vector in that scenario, alongside grids, renewables, electric vehicles, construction, and defense. Calling the whole move an AI trade would erase the larger electrical economy. Now the twist: even abundant metal cannot make a connection happen on time. The International Energy Agency estimates that grid constraints could delay around 20% of the global data center capacity planned for construction by 2030. That is the bottleneck hiding behind the metal story. A project can have chips, land, and financing, then wait because the surrounding electricity system cannot connect it fast enough. That changes what to watch. A mine can take years. A transmission line, substation, or transformer supply chain can take years too. But data centers can move from announcement to construction much faster. The practical race is not one metal against another. It is whether power equipment, permits, and connections arrive in the same window as the servers. Cooling belongs in the materials map as well. More concentrated compute means more heat moving through pipes, cold plates, pumps, power electronics, and backup equipment. Copper has a role here, but the larger lesson is architectural. AI shifts metals demand outward from the chip into an entire operating system of power and heat management. Copper moves in tons. The precious metals work in much smaller, more specialized layers. Silver has the best conductivity of any metal, so it belongs in a high-performance electronics conversation. The latest Silver Institute outlook expects a 2026 structural deficit of 46.3 million ounces. That is a market signal worth tracking. It is not a license to say that AI alone created the deficit, or that every silver product sees the same demand shock. The clean way to frame silver is as an AI tailwind inside a crowded demand picture. Solar, investment flows, jewelry, recycling, industrial cycles, and fabrication choices all matter. AI hardware may add support at the margin. It does not turn silver into copper with a different color. The scale, end markets, and price drivers are different. Gold is even more specialized. World Gold Council data put 2025 technology demand at 322.8 tons, down 1% year over year. Electronics demand was essentially flat at 270.4 tons. The Council says AI-related electronics supported high-speed computing. That is, demand support, not evidence that AI has remade the global gold market. Gold earns its place where reliability matters: bonding, contacts, interconnects, and high-value electronics. Yet the same World Gold Council report notes active thrift and substitution work as gold prices rise. That is the right mental model. AI can raise the value of tiny quantities without making technology demand the main engine of gold's price. The smallest markets can create the sharpest strategic risks. Gallium is the cleanest example of a small material with an outsized strategic shadow. The IEA says data center demand for gallium in 2030 could equal up to 10% of today's supply. It also says China accounts for 95% of gallium refining. This is not a bulk tonnage story, it is a concentration story. Germanium points to the network layer. The U.S. Geological Survey identifies it in fiber optic glass for data networking and telecommunications. That does not make germanium a giant GPU ingredient. It makes it relevant wherever a bigger AI campus requires more high-speed links, optics, and specialized communication hardware around the compute. Tantalum is a warning against lazy attribution. USGS estimates U.S. apparent consumption at 890 tons in 2025, up 58%. It is used in high-reliability electronic components, so it belongs on the specialist watch list. But that figure does not tell us AI caused the increase. Small markets demand extra humility. This is the distinction worth keeping. Copper is a throughput material, large volumes moving through a huge system. Gallium, germanium, and tantalum are precision materials, small volumes where a missing component can matter far more than its weight suggests. AI may strain both. It does so through completely different supply chain physics. So, where is the bottleneck hiding now? Follow the deployment clock. Here is the practical map. Copper has the clearest direct AI infrastructure exposure because it appears wherever power and heat move through the campus. Aluminum matters at the grid connection. Silver and gold support specialized electronics, but do not carry the same bulk demand claim. Gallium, germanium, and tantalum matter most where concentration, qualification, and substitution become the real constraint. Watch 3 clocks instead of one-spot price. First, grid interconnection and transformer lead times, because no connection means no live campus. Second, power density and cooling design, because each megawatt changes the material bill. Third, specialist material concentration, because a tiny qualified input can hold up a much larger system. That is a more useful AI metals dashboard. The final reality check is the IEA's 20% estimate. If that much planned data center capacity can be delayed by grid constraints, then the headline shortage is not one magic metal. It is coordinated physical capacity: mines, refineries, cable, transformers, substations, cooling systems, skilled labor, and permits arriving before the demand window closes. The virtual mind is physical. AI chips pull demand through a chain of metals, machines, and power systems. Copper is the broadest direct exposure. Precious metals are specialized support. The sharpest near-term gate is whether the world can connect metal-intensive AI campuses to real electricity fast enough. That is the layer to follow,